So that's where MathWorks focus. We are interested in that part of it, the watts. What is it that makes up the electric powertrain, and how can we improve the efficiency and reduce the cost of that?
On this episode of Embedded Insiders, Ken sits down with Tony Lennon, who works in product marketing for multi-domain system modeling at MathWorks, to discuss energy issues and data centers. Next, Rich and Vin are back with another Dev Talk, discussing the differences between MCUs and MPUs, and how to determine which to use in your design. Hello, everyone, and welcome back to the Embedded Insiders podcast. I'm Assistant Managing Editor Tiara Oliver, joined as always with our Editor-in-Chief, Ken Briota.
Hi, Tiara. How are you today?
I'm doing well. Very slow, overcast morning, which I enjoy.
That's nice. Always enjoy a slow morning when you get one.
Yeah. Tomorrow will be a bit busier. I guess I can do a recap next week, but tomorrow I'm going to visit Microchip here in Arizona. I'm actually in the same city as them right now, but the event is actually a bit further away. So
Oh yeah, that should be really interesting. I can't wait to hear about that. I, on the other hand, am next week going to visit Northern California. I'm going to be in Silicon Valley for a few days next week, meeting with a bunch of companies. We're going to be recording some video interviews, so watch out for those on YouTube, and some of them may appear here on this podcast as well.
I guess in the latest of news that I saw towards the end of my day yesterday, that kind of tumbled over into another topic, which is GAN, which is obviously something that we've talked about pretty often, but maybe not lately.
Yeah.
But I was just looking at how, GAN adoption has, increased because of AI and data centers. And I wasn't even thinking about how those two connect. Obviously, now that I read about it, it makes sense, but it wasn't really on my radar, and I thought that was interesting.
Yeah, it's I've been a fan of GAN, ha ha ha, and silicon carbide, SiC, for a long time. They're not the same, and they don't have all the same use cases, but they're similar in that they're able to handle much larger power capacity as materials, and there's some benefits to like temperature management, the thermal problem and things like that. So it's a really interesting material that is being used in sort of high voltage situations, and data centers are certainly one of the key applications that I think are just going to keep growing. I wrote a little bit about this about a month ago, back in July, um, because I saw, just some case studies, some trends talking about how how the transistor market is really changing to GaN in a lot of ways. A lot of the major players, Navitas, Infineon, ST, these guys are not the only ones, but they're making big moves. I mean, Navitas has built a whole business around it for sure.
Mhm.
And so I think it's really interesting tech, and we're certainly going to keep covering it. In fact, there's a video program idea that I've been developing and trying to figure out how I want to do it for like the last year and a bit. And the first episode of that is probably going to be about GaN because I think it's really interesting tech. I love
Also,
materials science.
well, I'm glad you do because you can help me understand it a bit more.
Oh, I there are better experts than I. and you should bring them on this podcast. So if
Yeah.
you're an expert in GAN out there, reach out to Tierra, get on the podcast, explain everything that everyone needs to know about GAN, SiC, and alternatives to silicon.
Yeah, and I was also still researching, couldn't find, my exact answer, but just wondering if GAN is gonna have like a better, I guess, environmental impact as opposed to silicon in its use
That's
in.
that's indetermined in as far as I know. The gallium nitrate, you're still dealing with um, rare earth materials. Gallium is not uh, un, it's still a mining process. It's still a
Yeah.
refining process. So like there is a lot of energy there. So how sustainable it is, I don't know. I
Mhm.
would suspect that it's not. Well, I don't want to speculate that much, but I don't know that it's that much better um, or worse.
Yeah. Well, with all this talk about AI and data centers, um, I think it would be great just a call to action to anyone out there listening, or we would love to have you on the podcast to discuss this. This is definitely something that's for sure going somewhere, and
Yeah,
it would be interesting to see how it'll affect things going forward.
absolutely. And uh, everyone out there should look forward to what I'm sure will become an upcoming story once Tierra figures out whether or not GAN is more sustainable and environmentally friendly.
Exactly. Stay tuned. Now, here's Tony Lennon of MathWorks.
Hello, friends, engineers, developers, and embedded professionals all over the world. Welcome to another segment of Embedded Insiders podcast with Embedded Computing Design. I'm Ken Briota, editor in chief of the aforementioned Embedded Computing Design, and I'm very excited to be here on this segment with Tony Lennon of MathWorks. Tony, welcome to the show.
Thank you, Ken. Appreciate being here.
The pleasure's entirely mine, and as they're about to find out, our audiences. Can you tell us a little bit about you and about MathWorks and what you guys do in case folks aren't familiar with you?
All right. So I lead the SimScape product area. It's a modeling software for simulating multi-domain electrical, mechanical, thermal systems. It's used often to develop control systems. MathWorks in general has a products, MATLAB and Simulink. I think your audience may know these products. Simulink is used for design analysis of embedded systems. And in the case of what we're doing lately is kind of a focus on AI data centers, where there is a big need for electrical power, also cooling. And that's where the SimScape products are very useful for them, for the different players in the market to model these types of systems.
Yeah, absolutely. And that's what we're going to be talking about today. And we'll see. This conversation might get a little bit spicy. I've got hot takes on the world of data centers, and we'll see if you've got some too, Tony. But the thing that I want to talk to you about in particular and is the idea of AI data centers becoming profitable. Now, the data business has been talked about as big business for a long time. Now that AI has sort of become the dominant technology in the data management business, we're seeing a lot of these data centers popping up. There's a lot of talk about how energy use and about water use, which we're not touching on today, but we're going to talk a lot about power and about watts in particular. I think you've referred to it as the watts problem. So can you give us sort of the core sort of issue that you're seeing out there and that we're going to talk about today?
Sure. It really is. You've heard NVIDIA talk about, particularly Jensen Huang has talked about, tokens per watts. Basically, his concern and what he's explaining is that you want to get as much compute power out of every watt you use. And every watt you waste means you're not selling compute. And so in that regard, the people who are speccing the data centers, the hyperscalers, are very interested in coming up with what we call the electric power train, right? What goes from the grid down to the actual GPUs, CPUs, everything that goes into those big rack servers.
Mm-hmm.
Also, the cooling, the power that goes into cooling all that, because that's one of the biggest areas of waste for these data centers. At the end of the day, what you brought up is really important. He described data centers as AI factories. And when you hear the word factory, I immediately go to the thought that, well, you don't want if your product starts moving towards a commodity and the price gets set by the market, the only way you're going to increase your profitability is, you need to reduce your costs, right? So that's where MathWorks focus. We are interested in that part of it, the watts. What is it that makes up the electric powertrain, and how can we improve the efficiency and reduce the cost of that?
Yeah, and it's sort of like a holistic system problem, I feel like, which so many embedded problems end up becoming system problems, where we've got not just to talk about generating enough energy to support the entire grid or just the data center, as it's becoming a little bit more common now, but also where it's being allocated, how it's being used, whether or not any of it's recapturable on the other end. To me, it seems like a systemic problem and a really complicated one. And so I'm wondering, what is the piece of it that you and your team at MathWorks are trying to solve?
Well, there's a number of parts to this. So if you think of the ecosystem, that's what I kind of call it. You've got the distribution system, the utilities generating the power. You've got the equipment companies providing, the electrical systems, which, power converters, transformers. You also have the companies providing all the cooling equipment, and then the hyperscalers themselves, the data center spec, the people who want to run compute. And so what we're looking at is, first of all, can we help the hyperscalers present a picture of how much power a data center is going to require, right? So because they need to be able to discuss with, the grids that they're connecting to, this is going to be the impact of our data center on your grid. They're also looking at, how much auxiliary power do they need to put on premise, right? Are they going to use gas turbines, diesel generators? Renewable would be great if they could get the credits for that. They want to have their own battery energy storage systems.
Hey, if we're going to go down a rabbit hole and talk about battery and energy storage, I'm here for it. It's a little off topic, but boy, do I have big opinions.
Well, but it's part of this. You brought up, how do I get the power, right? Because as these things, when they go into an inference mode, they're really drawing down, right? Then they transmit the information, and it's very cyclic. Well-known problem. The people who are providing the equipment, right? They're looking at new actual power conversion. We actually call it like low voltage DC, right? They want to go have a solid state transformer that can connect to, 34,000 kilovolts and drop that down to 800 volts DC. Because there's a lot of efficiencies. If they get rid of the classic analog transformers and move to digital, there's a tremendous efficiency gains there. And they're looking for every watt of power they can save.
I recently read, and this might not be correct, so please correct me if I'm wrong here, but I've read that there's some study still ongoing that says that some of the digital transformers might not be as robust as the old analog ones in terms of longevity and like life cycle. Is that what you've been hearing and seeing as well, or no?
I haven't heard anything about that. Okay. I hate to comment on something.
Well, no, it's fine. I saw one little snippet about it, and so I'm not at all endorsing the opinion. I'm just curious.
Let me put it this way. we have a customer, Siemens Energy,
Hmm.
right, who makes HVDC devices, right?
Yeah.
And essentially those are just, multi-level power converters. They've been doing this for decades.
Sure.
And, so this is just another technology in that vein.
Hmm.
Whether they, I'd be surprised if they came across something that they didn't understand, right?
Right.
It's,
Yeah.
so that it'll be interesting to see, but it could be the fact that they're using, some of like the silicon carbide type
Yeah.
power electronics, which is still it's in the world of power converters, it's still a new technology, but well proven.
Really
It's
exciting one, I
yep,
think.
yep.
I think it's a
A
really
lot of
interesting one.
efficiency gains there. Yep. So
Um, so in this sort of holistic system, where are the, I don't want to say weak points, but the places where an engineer, the facilities manager, the operator of a data center, the engineer who's working in there can prepare or potentially try to avoid the awful downtime. What are the parts of this that are the weak spots? Is it at the storage level? Is it transmission? What is it?
well, since this is still a relatively new area, and these are massive centers, right? They nothing that we've done previously or consumes this amount of power.
Right.
So probably the weakness that we when we talk to our customers, they talk about understanding how to recover from faults, right,
Mhm.
on such a large scale. With our software, we can actually model faults. They can go in there and say, okay, this is going to fail, and what would be the recovery? They can
Right.
develop state logic, supervisory logic to kind of figure out how to recover on that.
Hmm.
Now, I think that what we provide is the ability to simulate that whole powertrain against a number of environmental concerns, right? If you're
Yeah.
say you're using air cooling for water, okay, hot days, cold days, how does that impact the power usage of the data center? Start injecting faults and really do a huge what if study. So for us, we're the software you want to use to make sure that when you go to build this, it's going to be right. Another thing that, because there's new technology going into these data centers, um, our environment, Simulink, provides the ability to take a model from your vendor, your supplier, and bring it into your simulation. And we have ways to, help mask some of the IP. They can do something with a little less fidelity. They don't need full
Hmm.
switching on the power converter. Use some average value power converter, but it
Right.
gives the centers this ability to really understand how this thing's going to operate. And even then, once you have that, essentially a digital twin, that's what they're building. Um, they can, as they start to operate, they can start bringing in data and comparing. Okay, here's the inputs from the data center into the model. Are we getting the same results that we expected? And that will
Yeah.
help them troubleshoot some of the problem areas.
Yeah.
So a digital twin is great preparation for when you go into operation to say, hey, what we design, is it working the way we intended it?
Well, I'm a big fan of digital twin simulation modeling, so I love what you guys are doing. I think that the it's one of the most powerful applications of big data that engineers have at their fingertips is this ability to create realistic simulated models of almost any known condition. I think that's really cool. um and you mentioned something else that I think is really important to this discussion, and this might be getting into spicy territory, so I'll warn you here. But the idea of data centers making use of renewable energy rather than power grid energy, self generation, whatever, um, is I think fundamentally the answer, because they have a PR problem as much as they have an energy problem in the communities where these things are going in. If other people live there, they are unhappy about it. Is broadly the news cycle. And so I'm curious because I remember a couple of years ago at NVIDIA GTC when uh, NVIDIA and Jensen Huang was first announcing the Blackwell compute AI boxes, the servers, basically. And he said that it almost bragged, I would qualify it as bragging, that the water cooling system came in at near freezing and left at boiling. That's how much heat they were pulling off of these systems. To me, that says, well, why aren't we running a steam turbine off of this water cooling system on the other end? And also then cooling it, sending it around. So you then start the whole system with wind or solar or whatever. And then is that something we can simulate? Is that a realistic power solution? Is anybody doing something like that? Or is that sort of just not there?
Well, we've asked the same question, and you can simulate it. We have our software, you can, mix electrical and the thermal, the cooling loop. What we've been told is the energy you're getting back isn't high enough quality. I mean, you may be able to do some heating,
Interesting.
but it's not something that's going to, like a combined cycle, gas turbine, where they're taking the exhaust of a gas turbine and actually running a boiler. That's
Right.
very high quality. That's why that works. Almost boiling is not quite there for the type of energy recovery that would run a data center. It may be other auxiliary systems,
Something.
anytime you have a Delta T, you usually can do something with it,
Right.
but not at the level that the data center is going to need. But you bring up a great point about, these are hungry beasts. They're talking on the gigawatt scales where these things are heading.
It almost feels like they need their own sort of microgrid in order to run as it well efficiently while still being good neighbors and good citizens of the
Right.
area, right?
Yeah, that's true. And that's why I was mentioning that they there's a lot of companies getting very interested in providing generation on site.
Mhm.
And it will probably be a combination. And again, this is where we feel we have a great solution to help them do the what if studies, right? Not only can you run the simulation, you can run optimization with it, right? We have optimization tools within MATLAB that hook right up the Simulink and just let it run. Find the best solution. What combination? When should you be generating power? Maybe at peak. Maybe there's enough power on the grid, normally, but usually where any of these big loads are going to see the biggest challenges during peak power, right? It's
Right.
middle of the day, it's hot, everybody's running air conditioning, that type of thing. So it will, until they can find ways to pipe as much power as these data centers need. They're probably going to be doing a lot of on-site.
Tinkering almost trying to figure out the answers. Obviously the big player in that room right now is Microsoft and 3 Mile Island, and if they get that thing back up and running again, they'll be the king of self generation, I guess. It's a really interesting situation, and obviously, as you said, a developing industry for sure. Like, it's not like we haven't had data centers a long time, but not like this, not where the drain is, as I understand it, really uneven. Like, you're pulling a lot more energy when you're training a model than when you're just querying or running a model, right?
Mm-hmm.
And so you might only do training, a couple of days out of a month or something. And so that's when your big heavy draw is. And the rest of the time you're drawing some amount, but it's probably not that gig scale at that time. It's a really complicated problem. And if, as it appears, the AI data center growth is going to continue for some considerable amount of time in front of us, I think that simulations like you guys are able to provide, and those kinds of digital twins are how we're going to at least preliminarily answer a lot of these open questions. And I think it's really cool.
Yeah, you said something that reminded me of an article I read. That these data centers will be microgrids, not small microgrids, but they will be able to island if they had to. And the utilities really are going to start asking them to give them models. Tell us what these, give us tuned models, because, as you said, it's not an even power draw. I'm not a steel mill where I'm continuously, pouring. It's going to be not even cyclic is probably a generous word. There'll be spikes.
Yeah.
Something comes up in the news, and all of a sudden people start running queries, and you see big. And that's what the from our understanding, talking to some of our customers in the utilities world, they were like, it was when they first started seeing these appear, it's big load draws and go away. They didn't quite understand what was happening, and they quickly recognized that these data centers were a new animal on their grid.
Yeah. Unlike functionally anything else. I mean, even a big steel mill or manufacturing facility or whatever doesn't draw what one of these data centers draws at peak operation.
Right.
And so, it's funny because, and I'm sure you've heard these things, the most challenging power grid and power situation in the United States, people would say, oh, is it New York City? Is it whatever? It's Manhattan, or rather, it's not Manhattan. It's Washington, D.C., as I've always heard it, because you never know whether the Pentagon or the White House or Congress or whatever is going to suddenly need a lot of power all at once. You have to have these huge reserves all the time. You're gonna, so it's a very complicated problem. As I'm not an expert, I'm not an engineer. The audience knows that sometimes I've just read a thing and I'm wrong. That's what happens. But that seems to be a problem that every power grid, power company manager is going to have to start thinking about. I need to have reserves. I need to be ready, or I need to rely on the data center operators to manage their own reserves and be holding their own, so that if I tell them you can't have power right now, they have a backup.
Right. No, that's what we're helping them understand.
Yeah. And I mean, I don't think we have the answers yet as to where that sort of relationship will fall. It'll probably be different in every area. In some places, the power companies will tell the data centers, listen, sometimes we're going to tell you can't have the power, and you better have your own backups. Other times they're going to have a relationship where they are able to balance load and stuff and not have those kinds of conflicts. It's going to be very interesting to watch, and I look forward to seeing what kind of simulations you guys come up with. Where can folks find out more about MathWorks and about you out there on the interwebs?
Oh, obviously on our website, mathworks.com. If you go look up, we have a power systems area, and we talk about data centers. We talk about a lot of different electrical capabilities, from EVs to power electronics, power systems. It's an important area for MathWorks. We have some great customers out there who support us.
Absolutely. Well, thank you so much, Tony. It's been a real pleasure having you on and chatting with you and picking your brain today.
No, I love it. Thank you. It's a great topic.
Thanks a lot, Tony. And folks out there paying attention, if you haven't subscribed yet, make sure you do. If you're watching this on YouTube, thank you for joining us here for one of our video episodes. And we hope you'll come back often to check out all our shows, DevKit Weekly, and in case you missed it, the news show that happens every Friday. In the meantime, I've been Ken Briota, Editor-in-Chief of Embedded Computing Design, and your host. And I'll catch you next time. Have a great day, everybody.
Now, here's Rich and Vin in another Dev Talk.
Good afternoon. Welcome to Dev Talk with Rich and Vin. I'm Rich, and that's Vin. I'm Rich Nass. I am with Embedded Computing Design. Vin, introduce yourself, because we haven't really done a formal introduction in quite some time.
We have not. No, I'm Vin D'Agostino. Rich and I have been friends for years, and an engineer working in the embedded space and also consulting with companies adding technology. So I see it from many angles.
There you go. Okay. So one of those angles that I want to talk about today, I say this a lot. Back in the day, which makes me, I guess, sound old, but back in the day,
We are old.
I'm not that old. Microprocessors were introduced on a regular cadence, and there was this other thing that sort of had a little baggage with it that was an MCU, that was a microprocessor that had memory on board. And that just became the norm. But as we progressed into things with ARM and other types of IP and processor cores and things like that, the terms became a little ambiguous and were used synonymous. And so this is like a level setting podcast. Let's talk about what is an MCU, what is an MPU, and if we want to get into it, we could talk about GPUs and NPUs, but the purpose here really is what's the difference between an MCU and an MPU, and when to use one and when to use the other, and are they synonymous?
Okay. Well, they're not synonymous. They are complementary, I would say. And I think, we are old, you and I, at least older than a lot of, I would say, the average of our audience.
You said a few minutes ago I wasn't old. So which is it?
No, you said it. Didn't you recognize your own voice? That's part of being old.
I thought I was agreeing with you. Sorry.
When we got started in this business, there were no MCUs, and we were laying PC boards out with Mylar tape and X-Acto blades, right? And so all of the buses for interconnecting peripherals and memory and computing elements, if you want to call them that to start, were all done on 2-layer boards and exposed buses. And we were excited about having a 1 megahertz bus and worried about whether it might work or not, right? And at that point, everything was an MPU. Everything was a microprocessor. We didn't have the integration technology to put multiple things on a chip. And
Give
so
me
we
a
didn't have
timestamp for what sort of area you're talking about.
this is late 70s, early 80s, even late 80s, right?
Wasn't the 8051 an MCU that had an 8085 processor core? Did I get that right?
It was an MCU. I'm trying to remember what the core was. A lot of companies were trying to do this integration because it meant that they could start using the technology with people who didn't know how to deal with managing buses and stuff like that, right? The buses.
But MCUs sort of became a non-thing for a long time, if I remember right. And it was always, the processors were introduced by Intel, and then AMD would a year or so later would come out with something similar. But it was 8085, 8086.
Well, this is long before Intel CPUs for desktops. I'm talking about things like Motorola 6301s, which they actually did. I think that was the part they did in conjunction with Renesas. There was the 8051, the 8049 before that, the 4001, I think, was actually an MPU. And so it was a processor, and it was kind of loosey-goosey, and MPUs actually never really disappeared. I mean, look at the 6502. That was built by Rockwell. It was built by a couple of other people. It was in the Apple IIe. It was in set-top boxes. It was in a lot of stuff. It was the first processor that I released product with, right? And it was just the computing element and the bus management element, and memory was external, both flash. It wasn't even flash. It was light erasable programmable memory. So it was, the ceramic packages with the window, and you put them in the drawer with the UV light to erase them, right? That's how long ago. And there was SRAM long before there was dynamic RAM that had to be refreshed. So, a lot of that is the precursor to all this. And then, in fact, when MCUs came out, they were almost all windowed packages because you needed to program the memory, but you wanted to reprogram them. And so they were all ceramic packages. They were still expensive. And it was actually Renesas who did the first programmable plastic package. They called it the ZTAT part, and it was zero turnaround. So you could stock these things in their vanilla form, and you could have 20 different pieces of code for 20 different products, and you pull it off the shelf and you programmed it on the manufacturing floor, and that's how you were able to do it. You didn't have to mask things, and they put them in plastic packages so they were cheap.
Well, that's a pretty good segue, because Renesas is actually one of the ones who's in this MCU MPU industry. That's not the right word. They offer both. So let's fast forward to today. When is the right time to go MPU? When is the right time to go CPU? And just explain this, right? Is an MCU the exact same thing as MPU, just with memory on board?
No, in fact, it's
well,
not.
That's a really important point. So let's start there.
So the definition of MPU changed over time. Once we had these MCUs, how were MPUs going to differentiate themselves? And as programs got bigger, as operating systems came into place, there was a need to start virtualizing memory. So MCUs don't have virtualized memory. In fact, I would say in 99, maybe 99.9% of the cases, when you program an MCU, it's a single image, right? And it goes into Flash and it executes out of Flash.
Mm-hmm.
Now, when we started to need to manage memory to virtualize things, so individual programs or drivers or things could sit anywhere in memory, and every little program segment, if you will, started with address 0 just to make our lives easier for conversation. You needed to manage memory somehow. So if something was sitting at 2000 and you wanted it to believe it was sitting at 0, so all the relative and absolute references were okay, you needed memory management to be able to do that. If you wanted to restrict some area of memory from being written, so as you were writing variables, you couldn't write over your program, then that required memory management. And for most instances, MPUs are running code out of RAM, which means on startup, it's copying stuff out of non-volatile storage and copying it into RAM, and then it runs. There are what are called XIP solutions, execute in place, where the stuff is running out of Flash, but most of the time it's loaded into RAM. So the industry has evolved to use the MPU terminology for devices that have memory management units in them. In fact, if you look at parts from various companies, and Renesas is one of them, there are parts that have megabytes of SRAM or even dynamic RAM on them. They're still MPUs because they have memory management units in them. So the question really becomes, when do you switch from one to the other?
But that sounds like an obvious performance thing. If you're running, if you don't have to leave the chip to pull your data, you're obviously getting a lot better performance than if you have to go off chip to pull in your data.
Yes, for sure. That memory ended up on chip for very, very easy and quick access. These were typically things doing, well, let's see, some of the ones I'm thinking about from Renesas, for example, were used for infotainment in cars, where you need responsive screens, you need to be able to correlate touchscreen to what's going on the screen right now. As you're moving around with GPS, you need to be able to move maps around relatively quickly. The screen certainly moves faster than the tires on the road, but stuff like that. And certainly as you're dealing with cameras and then autonomous driving and everything else, that gets into a whole nother class. But certainly memory performance and access to memory is incredibly important for those kinds of applications, as is AI, which is what we talk about a lot.
And from a cost perspective, the MCU versus the MPU, is this where the marketing guy says, well, you have to look at it from a system perspective?
There is the rare MCU that approaches the performance of an MPU. So it's hard to say. I mean, MPUs for sure are more expensive. Most require, for example, power management ICs because you need to bring up rails for memory, for core, for peripherals in a certain order within a certain amount of time. You typically are not running internal clocks, so you have clocks that are external. And so they are more expensive and more difficult to work with. In fact, a lot of people working with MPUs are buying SOMs unless their volumes are really high. And the SOM has both non-volatile and volatile memory on it. It has the MPU. It has even some peripherals in some cases, and has the PMIC and the clock stuff on it. So it is like a really huge MCU, except that it's loading stuff into SRAM on power up, right? And it has incredible performance, and it can run. I mean, for example, you can't run Linux. You can't run what people think of as Linux on a non-virtualized machine. You certainly couldn't run Windows CE on a non-virtualized machine. That was a big deal, and that was one of the things that pushed a lot of people into MPUs that could have done solutions with MCUs because they wanted this windowing UI, and they were using Windows CE. And that I remember being at a WinHack and them talking about, oh, you don't need a lot of resources. You just need 128K of space in a virtualized memory. And I'm like, you know, people who are working on small parts like an RA0 or a PIC or whatever, they look at 128. They looked at 128K in the late 90s and early 2000s as, holy crap, what are you talking about? Right. And now you can find that much memory on like an R80 or really small parts. So the world has certainly changed.
And then to finish this, NPUs, GPUs are always used alongside an MCU or an NPU, not as a standalone, right?
Typically not. You know, those MCUs in many cases are being used to do system management. They may be doing power management. They may be monitoring batteries or something like that. You're not going to be wasting cycles of a GPU to determine how much battery life is left, right? Or to dim the backlight of something. So, and there are interface specs. If you're building a standardized system, there's interface specs to MCUs that are managing all that behind whatever may be running the computing. You know, GPUs started out to run very fast, short cycled instructions for moving things around in memory. You know, if you remember the old bit-blit tests and stuff like that, where you're moving things around on a screen to show performance. And then there was this home where a lot of that same performance was valuable to doing AI applications and to do even signal processing, right? For a while, there were companies like Fujitsu, who I think no longer even makes parts like this, that were making architecture specific MPUs for doing digital signal processing because they needed these extra instructions. Now the DSP extensions are in the ARM core extensions, right? And ARM core instruction set. And so a lot of these streaming data applications for AI are making use of the DSP instructions, and you don't even need something special. If you need to do neural networks, NPUs are the things to do that very well for you, right? So there are these niche products. We could look at tons of other little things that people are doing, but in the end, for general computing, if you're looking at MCUs and MPUs, the differentiation is memory management, and the virtualization of memory, and the fact that in most cases, peripherals and some part of memory is off chip. Whereas in an MCU, you might have a peripheral that's specific or a sensor that's specific off chip, but you are picking them because you want a certain A to D, because you want a certain memory size, because you want certain types of timers to do motor control, because you want certain D to A's, and those are all integral to the chip itself. So
just because NVIDIA says that everybody needs a GPU, that might not be the case.
That is absolutely true. That is
Very good.
absolutely true.
Okay. Well, this was really good. This was educational for me, and I assume it's educational for the audience as well. So thank you very much, Vincent.
No problem. My pleasure.
Until the next episode, that was Dev Talk with Rich and Vin.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.